Okay, ready?
Yep, go ahead.
Okay, cool. So, hi everybody, thanks for coming. My name's George, and I'm going to be giving a talk on a principled design of capabilities in Pony. So this is a presentation based on my master's project at Imperial, supervised by Sophia and Sylvan, who developed the original formal model for the Pony language. This is just going to be a very brief overview. If you're more interested in stuff like this, feel free to get in touch afterwards. And also feel free to ask questions throughout, because this material is quite dense at times, so more explanations are probably needed in places. Okay, so starting off with an introduction to Pony, I would hope that everybody in the audience probably has at least a vague idea of what Pony is. So we're in an actor model language where actors encapsulate threads of execution. They execute concurrently with their own mutable state. They can pass this state between each other in the form of message passing and behaviors. And obviously this can lead to data races when you have an object which sends its data, mutable data, to another actor, but the original actor maintains a reference to this object. So you have the possibility for one actor modifying a message, modifying an object, while the original actor has the possibility of reading or also modifying the same object simultaneously. So to solve this, Pony augments the type system with a system of reference capabilities, which you probably already have a vague idea of seeing around in the Pony language, things like ISO, transition, etc. And this is to ensure that data races cannot occur. So at compile time, we know for sure that there is no possibility of any data races occurring in the language. So, but how do we know this? We know this because there's a formal model of Pony that explicitly lists out all the possible cases, and through analysis, we know that there's no way that this can occur. So my work is based around extending the existing formalization of the language, which was developed by Sophia and Sylvan, and it was in two main areas. So firstly, we add support for additional language features, so inheritance tuples, union intersection types, as you can see there. The idea was originally to also add support for generics, but due to time constraints, obviously, along with other university work and things like that, we never got the chance to. But I think that we've developed a good framework to build on in that respect. The second part, and the part that I'm going to be focusing on today mostly, is to simplify and enhance the existing formalization. So the formalization that was originally developed had a lot of special cases and a lot of magic that wasn't really explained except by it worked. So the principled design comes into that, where we tried to formalize these things and explain why certain things happened. So the 3 points that are listed there, hopefully, well, they don't mean anything at the moment, but hopefully by the end of the talk, you at least have a vague idea of what they mean. So before we get into the finer details, we first need to take a brief reminder on Pony's actual system of capabilities. So as you'll know, capabilities are associated with any actor or object type in Pony or trait or interface, for example, a foo ISO or a bar ref. So in the model, we use the symbol kappa, which you can see on the top right, on the top left, to indicate a capability, which may be one of the 6: ISO, transition, ref, val, box, or tag. And these capabilities are based on what properties are denied to aliases of objects. So I've got an example here. So a foo ISO, an object with an alias of foo ISO, the owner of that alias is denied the ability to make any additional aliases of that to that object. And that's because ISO is short for isolated. It guarantees that it's the only alias in the entire program whatsoever to that object. So if we list out what properties are denied locally on the left across one actor in the program, and also what properties are denied globally across many actors, we can form a table like that. So if we deny any global aliases, so if we restrict the object to only having aliases within one actor, then it's perfectly fine for you to mutate it, because there's no chance that any other thread could read it simultaneously. If we only deny global write aliases, so if we only deny mutability, then we only can guarantee that the object itself is immutable. We can only read from it, because concurrent reads are fine, but if we were able to modify the object, then that would obviously be bad. And finally, if we allow any global alias, then it's just opaque, because we have absolutely no ability to read or write anything to it. So we can start to fill in this table. So starting with our example before, ISO, we have that an ISO object denies all global aliases and all local additional aliases to the one that we already have. So what this means in practice is that there is no other alias in the entire program except for the one that we already have. So we can see this on the diagram on the bottom right, where we have alpha means actor, and iota on the bottom means object. So you can see we have a arrow, which is an alias with capability ISO to this object. We also have two other paths, which at the moment are crossed out because there's no possibility of any other aliases existing in the whole program. Our next thing is our next capability is transition. And what this means is, in this case, we're denying all global aliases. So we're still mutable, but at the same time, we're only denying global write aliases, so only mutable aliases.
Sorry, George. Ricardo, could you mute your microphone, please?
Sorry, yes.
Carry on, George. Sorry.
Thank you. So going back to transition. So we deny all global aliases. So we're guaranteed that we're the only actor that has aliases to it. So of course it's mutable. And in this case, we're denying local write aliases rather than everything, as in the case of ISO. So what this means is that we are the unique mutable alias in the program. So nothing else can mutate this object except for the alias that we currently hold. There might be other immutable aliases within the same actor. And what this means is there might be other box aliases, as you can see in the diagram on the bottom right. That doesn't work. Our last mutable alias capability is ref. So this, once again, denies all global aliases because we want it to be mutable. But in this case, we allow any local aliases to the object. So as you can see on the diagram again, we have an iota and we have one ref alias, but then we also could have any number of immutable or immutable aliases through some other path to the object. Once again, we still can't have any aliases from another actor. So this means that we could have any number of aliases that mutate the object, so it's not unique in any way, except for being the only actor that can mutate it. We have val, which is our first immutable capability. So in this case, we are denying write aliases, so mutability both globally and locally. So what this means is that there's no possibility of this value ever changing because we're guaranteeing that nothing can change it. There's no alias that could mutate it. And as a result of that, we are allowed to have a val or a box, any immutable alias, both locally, or indeed you could have a val or a box coming from another actor because you're guaranteeing that nothing could possibly change this object while you're observing it. Box is very confusing at first sight because, once again, like val, we're making it immutable. So we're denying the possibility of anything in another actor modifying it. However, we are allowing something in this actor that the box is currently referencing, the possibility of there being a mutable alias to it. So if you see on the diagram, we've got val or box from another actor, which means that it's immutable. So that can't possibly change, which is good because that's what we wanted to avoid. But there's the possibility of having a transition or a ref from the same actor, which could mutate the value. Now, initially this seems a bit wrong because there's the possibility of having a mutable alias to the object And at the same time, there's the possibility of having an immutable alias, so a read-only alias from another actor to the same object, which is obviously a data race. But in practice, this is checked by, in practice, you pairwise check aliases. You pairwise check capabilities. So although it's fine for the box to coexist with a valor box from another actor, it would not be fine for the transitional ref to coexist with the valor box from another actor. So in practice, this is safe, despite first appearances. And finally, to fill in the table, we have tag. So tag allows any other alias to exist in the entire program. So there's the possibility of there being an ISO or anything, either in the same actor or in any other actor for that matter. So this once again seems a bit pointless on first glance because, well, it's opaque, you can't do anything with it, so it's a bit useless. Maybe, well, it turns out that tag is actually very useful for actors themselves. So because actors have their immutable state, they can refer to themselves as ref, so they can mutate everything they own. But that means that in practice, any other actor, if it wants to refer to a different actor, can't have it can't have write or read access to the state of that actor. So in practice, what it uses is tag. And it turns out that tag is fine for things like message passing because that doesn't mutate the state of the object explicitly. It just tells the actor to, at some point, whenever you're done executing the current behavior, to mutate the object. So it turns out that tag's very useful for actors. Finally, you'll notice that ISO, val, and tag, which are the things on the diagonal, are underlined. This means that they are sendable to other actors. So you'll notice that this is where, because it's on the diagonal, it's where what you're denying locally is equivalent to what you're denying globally, because then it means that you can just shift this to another actor and you're maintaining the exact same guarantees as before. So now we get and start making a few charts or tables. So I'm not expecting anybody to remember any of this because there are too many of them and it would be completely impossible. And I can barely remember them myself, so that's fine. But what this basically is, this is local compatibility, which, as you can see on the top, we denote with a squiggly thing and an L underscore for local compatibility. So what this says is what capabilities can two aliases have pointing to the same object in the same actor. So we have, this is derived from all the examples we saw before. So for example, in this case, we have boxes locally compatible with transition, ref, val, and box, and so on and so forth. And you can see that on the chart. So for example, if you have two ref aliases to the same object, then that's perfectly fine because they both don't assume uniqueness of any kind and they're both mutable and both in the same actor, so everything's fine. And you can see that on the table. But if you have two ISO aliases, then that's not fine, right? Because ISO guarantees that it's unique in the entire program. So if you have two aliases, then that's not unique in the slightest. That breaks most of the guarantees offered by ISO. So that's not fine. Similarly, we have a thing called global compatibility, which is exactly the same notation, but with a G instead of an L. And what this is, the same thing, but between two different actors. So for example, in this case, I have two actors alpha and alpha prime with two capabilities, kappa and kappa prime, pointing to the same object. And in practice, what this is it's obviously if something's immutable, the only other aliases to the object in another actor must be something that cannot access that actor at all. It can't even read from it because that would give a data race. So what it means is you end up with only the immutable capabilities, val and box, as well as tag with anything because tag doesn't make any guarantees. So for example, here we have two immutable aliases. We have a val alias and a box alias. And these are fine because there's a tick mark there and they're both immutable. But our previous example where we had two ref aliases is definitely not fine because that means that both of them could try and simultaneously mutate the state of that object, or so one could read from it while the other one was writing to it, or something like that. So that's our basic things. We now go on to aliasing. So if you've used Pony for very long, or probably more than an hour or two, you'll be familiar with the exclamation mark operator in the type system, where you can, and also if you've seen many error messages, you'll see ISO exclamation mark is not a subtype of box or whatever. So we use it's the same concept, except in this case we're referring to it by a plus rather than an exclamation mark. So if we have this example I have here, where we have an actor which has an alias x with capability kappa to an object iota, and then we do y equals x. So now we're making a new alias, which is in bold there, y, with another alias to the object pointed to by x. But we need to know what the capability that y should have. So could it be kappa? Well, no, right? Because if kappa was ISO, then we'd now have the state where there are two ISO aliases to a single object. And as we saw before in local compatibility, that's most certainly not fine, because that breaks most of the guarantees of ISO. So what instead we do is we use this notation plus kappa to indicate that we're adding an alias to kappa, and this denotes the capability that we get back from such an operation. So we give y the symbol plus kappa, the capability plus kappa. Aliasing an ISO, because ISO guarantees complete uniqueness, read and write uniqueness, the only thing we can give is tag, which is why when you get that error message, ISO bang is not a subtype of box, it's because ISO bang is tag. And they should really write that, but never mind. And similarly, the alias of a transition is a box, because transition guarantees write uniqueness. So if you alias that, you can't have any mutability right whatsoever. So the only thing you can give is box or tag. Box is better, so we give that. And everything else aliases to itself. So ref, val, box, and tag all alias themselves, because they don't make any guarantees about the uniqueness of their aliases. So with that out of the way, we now need to take a quick diversion through subtyping. So I mentioned this briefly earlier with boxes. So tag is not a subtype of box and things like that. So this is how subtyping looked in the old system, in the system that was developed by Sophia and Sylvan. So it's reasonably straightforward. ISO is the most precise, makes the most guarantees, so it's at the bottom of the subtyping relationship. ISO is a subtype of transition. Transition is a subtype of ref and val. Ref and val are completely distinct because they make very different guarantees, because ref guarantees that it's in one actor and allows you to make any number of mutable aliases, while val guarantees that there are no mutable aliases whatsoever. And then these converge to box, because box makes very few guarantees, and both of them are compatible with ref and val. And finally, box is a subtype of tag, because tag makes no guarantees whatsoever, so it's at the top of the tree graph. This is good, except in practice, we find that a lot of lemmas we would like to hold, such as viewpoint adaptation, is preserved through subtyping and various other things that I won't get into. There are various lemmas that we would like to hold that would make the job of proving the model a lot easier, that don't hold in this model. And that's mostly to do with small reasons that don't actually affect the end user. So in practice, what we would actually want is something like this, which looks very different. Well, the box is still a subtype of tag. Ref and val are still subtypes of box. The main important bit that we needed to change was transition and ISO, as they stand, can't be subtypes of ref and val, and ISO can't be a subtype of transition, because this breaks many of the things that we wanted to hold. But of course, if we used this, then this would pose a problem, because if you have an ISO object at the moment, you can consume it and then transform it into a val or whatever you like. But in this model, you wouldn't be able to do anything like that, which is obviously a massive blow to the type system. So to get around this, what we introduce is the notion of extended capabilities, which we denote by minus instead of plus, to indicate that we remove an alias from an object. So we have two cases of interest. This is ISO and transition, once again. We say that ISO minus, so ISO, which guarantees that there's one unique alias in the entire program. So then if we remove an alias from that, we say that there are no stable, in inverted commas, aliases in the entire program. Now, that's different from saying that this object is garbage, because it could be that it's about to be assigned to something. So what we're saying is there are no named aliases to it in the entire program. For example, I've just consumed an ISO or something like that. It's not saying that it's useless, because it could be about to be used for something else. It's just only got a temporary reference at the moment. Similarly, we have transition, which says that there are no mutable aliases, no stable mutable aliases in the entire program. So because there are no mutable aliases, we can introduce a new mutable alias and make it transition, or we can introduce any number of mutable aliases and make it ref, or we can maintain that there are no mutable references and make it into val, which maintains what we wanted originally and what's actually implemented in the compiler, where you can transform one capability into another by consuming it.
Question, George.
Yes.
I just want to make sure. So the minus here is equivalent to the hat in Pony source code, right?
Yes.
Okay.
Yes, that's what I was going to say. It's exactly, almost exactly the same.
Okay.
The main caveat here is that there is no ref ephemeral.
Okay.
Because, as it turns out, ref ephemeral is more or less completely useless, except for maybe some edge case that I haven't considered. So
maybe I should send you a couple of those edge cases later.
maybe.
I actually have a couple in the code.
Okay, feel free.
Cool. Awesome. Sorry.
No, that's fine. One of the bugs that I found, which I'll get onto later, was a result of some weird ref ephemeral stuff, which not the root cause of it, but it introduced some weirdness. But anyway, moving on. So we have our original 6 capabilities, kappa, and to denote that we may include ephemeral capabilities, ISO minus and transition minus, we now use lambda instead. So lambda just means any of the 6 capabilities or these 2 new ones that we've made up on the spot. So we can introduce these into the subtyping relationship, which now looks quite scary, but it's more or less what we had originally. It's just we've now introduced ISO minus and transition minus at the bottom. So just to quickly explain this, ISO minus, since we have no aliases in the entire program whatsoever, we can do absolutely anything we like with it. We can make it into an ISO object once again, or we can make it into a transition, we can make it into a ref, we can make it into a val, and absolutely anything. Similarly, for a transition minus, since we guarantee that we have no mutable aliases, we can make it into a transition or a ref or a val, whatever we like. We can't make it into an ISO because transition minus only guarantees that it's got no mutable aliases. It doesn't guarantee us anything about whether there are any immutable aliases, any read aliases in the rest of the program. So with that in place, we can now define unaliasing, which is the hat, which is also the hat from Ponyland. So once again, we have our example where an actor has an alias X to an object with capability kappa. And if we were to do something such as consume X, we now have that this alias X has been destroyed, which we can see by the slashes through it. And instead we've got a temporary, which we use T instead of X for. And in this case, we could actually give this just the capability kappa, because that's fine, that fulfills all its guarantees. Except we can actually do better than that. And in practice, what we use is we use the notation minus kappa to indicate that we've removed one alias from kappa. So once again, this is a very stupid translation just because that's how we defined it. ISO minus, I got it wrong, taking away an alias from an ISO gives us ISO minus, and taking away an alias from a transition gives us a transition minus, simply because that's how we defined it. We defined the minus appended to a capability as just one alias removed. And everything else stays the same because, once again, we're not making any guarantees about uniqueness. So if we remove an alias from a ref, say, then we've started off with any number of mutable aliases. So consuming one of them doesn't actually give us anything more strict, more guarantees. So in practice, we can just make them be the same. So now we can get on to viewpoint adaptation. So viewpoint adaptation is denoted by the arrow in Pony in the compiler. So a dash and then a greater than symbol. So it's usually how this sees something or how box sees something or something like that. And indeed, this is what we define it as, although it's a triangle instead of an arrow, but more or less the same. So if we have an object which is aliased from an actor as X, so we have X which has some capability lambda, because in this case we might have an ephemeral, we might have a temporary object, so we're not sure, we're just going to call it lambda. And this object has a field F which has a capability kappa. Now it's kappa instead of lambda in this case, because if it's a field, then we know there's at least one alias to it. You couldn't possibly assign to a field which has an ephemeral capability because, well, you have an alias, a named alias, because it's the field. So that's pointless. So what we want to know is if we were to do a field read operation, so for example, x.f, then what we end up with is we have the result of that execution is a temporary object which points to the field object. And the capability of this temporary is the viewpoint adaptation of lambda and kappa, or how lambda sees kappa. So originally, when I started my project, this was defined in a table, a massive table that looked something like that. But the problem is that table was mostly derived through examples. So you would sit down, try and list out any possible example you could think of to demonstrate why something might or might not be able to be this capability, or why this is too strong. And eventually you might find one, or you might unfortunately think that it's fine and then go through a 100-page soundness proof, and then at the very end you'd realize, oh wait, no, that can't be that, or something like that, and then you'd have to go back, change it, and start all over again, something like that. So where the principled design comes in is mostly, so we went through and basically distilled down all of these examples into a set of rules which describe what properties need to hold as a result of reading a field. And I'm not going to go through them because they're not particularly exciting. They are mostly just derived from examples, but they're much easier to work with than just trial and error. And also you can plug this into a Prolog interpreter or a theorem solver, something like that, and you can actually get it to tell you whether your definition works, which is great and much improved over the original version. So what this gave us was a table that looks something like that, once we've added ISO minus and transition minus into it. And once again, please don't remember this because it would not go well. But the main thing to take away from this is that as a result of formally modeling this and from distilling down all these examples and modeling them and throwing them through Prolog, we can actually improve significantly over the model that's currently implemented in Pony. So we can actually be more general in what we give back to the user and give fewer restrictions. So for example, if going back to the slide, so if in this case lambda was ISO, so if I had an ISO object and kappa was ref, so if I have an ISO object with a ref field, and in Pony as you know it today, if you try to do x.f, that will give you a tag. So you won't be able to do anything whatsoever with that. But as a result of modeling this, we realized that, hang on a second, how ISO sees ref can actually just be ISO, which is very confusing on first thought, because we've started off with ref and now we're giving something more precise back than what we started with. But it turns out that the guarantees that are made by the ISO object itself can give us more information than just the field type itself. So we are able to do more things than the original Pony compiler. Another very interesting part of my work, so we introduced this notion of extracting viewpoint adaptation. So we've talked about field read with the normal viewpoint adaptation, but we haven't talked about field write, which in Pony returns the old version of the field. So if I do something like x.f equals y, we've got the same example here, and then we overwrite this field, and you can see the field has been crossed out because we've destroyed that alias. And now what we've got back is, as in Pony, we get the last assignment to the object. So we've got back a temporary object with some capability. So in the old model, what this was the unalias of normal viewpoint adaptation, which we realized by splitting this out into a separate operator rather than using the existing one, we could actually once again get something more permissive and place less restrictions on the user. So once again, we've got a bunch of rules that are not good to remember. But these ones, once again, you can throw into a Prolog solver and it'll give you out the actual definition of the table. So, and here's a table once again, and once again, we can actually make improvements over the existing definition, what we would have gotten from just using standard viewpoint adaptation. We can improve on this by splitting this out into a separate operator, and this gives us slightly more freedom to work with Pony's type system rather than shouting at it. So using those, we now have something that describes what we get from making new aliases to fields, what we get from making new aliases to variables, what we get from overwriting variables, and what we get from overwriting fields. So using all of this, we can now go and describe what it means for well-formed visibility to hold. So what is well-formed visibility, first of all? Well-formed visibility says whether a heap is data race free, basically, in a very straightforward manner. So we wish to check that a heap, a collection of actors and objects at a certain point in execution, is well-formed, and that no data races can occur in this state. So, for example, to use as our running examples, we have two heaps here. So the one on the left, you should notice is really quite unsafe. Just from our previous example, we have two isolated aliases to the same object. So we have x1, which is ISO, and x2, which is ISO. So obviously these both make guarantees that they are the only alias in the program to this object, which is clearly untrue because we can see one that's not. And similarly, we have the heap on the right, which looks quite a bit better. This one looks safe because we have one alias to iota1, which is an ISO, so we have no other aliases to it in the entire program, and it's true, we don't. And this has two fields. So the first field is f1, which is ref, and the second field is also ref. And this also seems fine because ref allows any number of mutable aliases in the program, and there are two of them, but that's fine. We can allow any number of them. So that one seems safe. So we now need to try and conjure up some definition that would describe these heaps as unsafe and safe, respectively. So as our first attempt, let's say that any path through the heap using viewpoint adaptation as needed must have a locally compatible capability. So if we take the left heap, for example, we have our first path, which is x1 and ISO, and then we have our second path, which is x2 and ISO. fairly straightforward. And this works fine because our ISO is not locally compatible with ISO. So we mark that heap as invalid, which is what we wanted because that heap's horribly unsafe. But when we come to do the second heap, you'll not recall at all, but that's fine, that ISO sees ref as ISO in our new model because we've managed to make that more permissive. But in the same sense, we've also broken this definition, which is unfortunate because we have ISO sees ref as ISO and ISO sees ref again through the other field as ISO as well, which then makes this heap invalid, and that's not what we wanted. So we'll have to try something else. Our second attempt says that all heaps have to have locally compatible paths after one alias has been applied to one of the capabilities. So this maybe doesn't make very much intuitive sense, but it helps if you imagine that a heap is actually perfectly fine in the state it's in until you attempt to make a new alias to the object. Because if you're making a new alias or you're destroying an existing alias, that is the actual act of mutating the object that makes the heap unsafe, because that is the very essence of a data race. So if we make sure that it's safe to be locally compatible after one alias, then maybe that makes sense. But unfortunately, this no longer works for the left heap because we have two ISOs, but the alias of ISO is tag because ISO guarantees complete uniqueness, so tag's the only thing we can give back from aliasing it. And of course, since tag makes no guarantees, then tag is locally compatible with ISO, which makes that heap valid, which is obviously horrifically wrong. So we know we're going to have to try something else, but just for the sake of completion, let's check the right heap. And the right heap actually works for the same reason, because we have how ISO sees ref as ISO, and once again, taking the alias of an ISO gives us tag. So that works because tag is locally compatible with ISO, but that's not really much consolation because we broke our first example. So our third attempt, and the one that actually works, and the one that's currently in the model that I developed, is to recognize that we've now defined not only how we read aliases, but also how we overwrite aliases through unaliasing in the case of consume, and also through the extracting viewpoint adaptation through field write. So if we take our left example once again, and we allow the path to perform unaliasing, so say we did consume x1 and consume x2, then instead of just being ISO, these are now ephemeral ISOs, ISO minus. And the alias of an ephemeral ISO is just ISO itself, because that's how it was defined. And of course, ISO is not locally compatible with anything except tag. Of ISO minus is in tag, so it's not locally compatible. And so we mark this heap as invalid once again, which is what we wanted, which is great. And the great thing is this also works for the right heap. So say we were doing x.f1 equals y and x.f2 equals z or something like that. Or, for example, x.f1 equals y, so overwriting f1, but just reading x.f2, just normally. So the nice thing here is that we defined the extracting view. Although we defined field read x.f1, how ISO sees ref to be ISO, if you were to overwrite a ref field, so how ISO writes ref through extracting viewpoint adaptation, that gives tag instead, which is great because this means that if you were to try and perform a field write, ISO writes ref as tag, and tag is locally compatible with anything, which works fine. And if we were to try and do field read instead, x.f1 is ISO, and ISO aliases to tag, so once again we're fine. So just to summarize, our first attempt was local compatibility, which worked for the first heap. If we then add an alias, then it only works for the second heap. But when we combine the second attempt, so if we have aliasing along with the possibility of unaliasing, which kind of cancels out the aliasing to some effect. Combining it with unaliasing and extracting viewpoint adaptation, then we can recover the first case, and suddenly we have something that actually works properly. Now, obviously, we've gone through a lot more iterations than this, but that was just a brief illustration of the kind of things that we attempted. So, oh wow, that's faint. So we have, this is the actual definition of well-formed visibility. We have 3 cases, which, once again, there's a lot of symbols which aren't important for this presentation. The first point we have is that 2 different actors, so 2 actors, must have a globally compatible view of any object that they both have a path to, which makes sense because that's just our definition of global compatibility. So any 2 actors see the same object either through normal viewpoint adaptation or extracting viewpoint adaptation or aliasing or unaliasing, must see the object in a globally compatible way. So they must both have an immutable view of that object. Our second case, which is the one that we were describing just now. So if we have an object that is seen through some capability lambda, and we have another object that's seen through some capability lambda prime, this is once again using extracting viewpoint adaptation or unaliasing or whatever, then we require that either these things are locally compatible after one alias, or we have a case where these paths may interfere in some case. So if I just quickly flick back to this example, if we were to say do unaliasing on X and then read the field in both cases, so do x equals y.f1 and x equals z.f2, then those would both give ISO minus, and then that heap would be marked as unsafe. But if you were going to overwrite the value of x, then that would affect the other path, because then you wouldn't be writing to the same object, because you'd be writing to whatever was just written. So we have this condition that says the paths may interfere in some way, and then we discard that case because those aren't cases that we care about. And finally, we have a third case, which handles the case of temporary objects. So because these are unnamed, they have slightly weaker guarantees, and these have to be modeled slightly differently, but we don't discuss those today. So I've talked about all of these things, but I haven't actually said why they might be useful. Why do we even want a new definition of well-formed visibility in the first place? Well, first and foremost, it's much easier to reason about than the old definition. It's significantly simpler and has a lot less magic and inverted commas, a lot less special cases. It's much simpler to prove that this definition is preserved. So what that means is if you're executing a program and your existing heap is well formed, then no matter what you execute next, you're guaranteed that well-formedness will be preserved, which is important because that means that if I start off with a program that has no data races, i.e. because there's nothing in the program because you haven't started running it yet, then you guarantee that through the whole execution of the program, then there are no data races. And finally, relating back to the rest of my work, it's also much easier to extend to handle things like unions, tuples, intersection types, and inheritance, and hopefully eventually generics. That would be nice. Whereas the original model was not extensible at all, which is why we had to get rid of it and replace it with something different. And just to emphasize, on the left, we have the old definition as presented by Sophia and Sylvan in a paper. And you can, obviously, I'm not going to try and explain it, but there are a load of special cases and it's just longer in general. Whereas this definition is a lot more compact, easy to understand, for me at least, and so on and so forth. It just makes our lives easier. So now I'm just going to move on to a quick tangent and talk about bugs in the compiler, because it seemed like something that would be interesting to talk about to people that actually used it. So we're going to start off with a bug with intersection types. So intersection types in Pony are denoted with the ampersand symbol, and are used to say that a class may implement a number of traits or interfaces simultaneously. However, the interesting thing here is that an alias, which is an intersection type, does not necessarily have to have the same capability for the two components of the intersection. So for example, here we have a data ref and a data val. Data is just some arbitrary class I made up. So we have one side of the intersection type which says that I'm allowed to make any number of mutable aliases in the program. And we have another side which says, I'm immutable, you can pass me to anything. So this is horribly unsafe because you can just take out the val part, send that to another actor, and now you have another actor able to read this data while you maintain the ref part of it and can mutate it locally as much as you want. So classic data race. And this was allowed originally because the recovery and data.create, the constructor, returns an ISO ephemeral as it would because there's no aliases to it in the entire program. But the problem is that ISO ephemeral is a subtype of ref, as it should be, and ISO ephemeral is a subtype of val, as it should be. But the problem is that when checking for subtyping of intersection types, there was previously no criteria about the combination of types that you find in the intersection. They were just completely independent from one another. So what we ended up doing was introducing some checks, and this is fixed in the Pony compiler today, as far as I know, to make sure that the combination of types that you end up with in an intersection are safe. This combination of capabilities, more importantly. And the other one I'm going to talk about is tuples and recovery, because recovery is always fun. So this is where I get back to the ref ephemeral stuff, because it's slightly confusing at times. So in this case, once again, we have class data, and we have a variable, which we have data, which instead of an intersection of ref and val, we now have a tuple of ref and val, which is the same case. We can still send the val half off to another actor and maintain the ref half locally to modify it and cause data raciness. So we get this from a recover block. And inside the recover block, we can simply create a new data, which we just give ref, because why not? And then what we would do is just consume data twice. Data prime, sorry. We can just consume data prime twice, and this would give back a tuple of ISO ephemerals, which is already very, very broken, because that's saying that there are two things which both guarantee that they are the unique alias to the object in the entire program. And we have two of them, so that's already horribly broken. And however, if we try to do this naively, then the Pony compiler will complain at us, because it will say, but you can't you can't consume the same thing twice in an expression, because that's bad, that's horribly broken. But what we can do is we can simply just assign it to another variable, so data prime prime, and then we can consume these both at the same time, and that gets around that problem. So that's an issue, but that's not really the main thing. The main thing is that recovery of a tuple in general is a very, very bad idea. And there's very few cases where you would actually want such a thing, because a recovery block allows you to say, I'm going to construct this object in a special environment, in an isolated environment, so to speak. And then by throwing away that entire environment, I can promote this object to give it more capable, a more precise capability, so up to ISO or something like that instead. Yeah, and I'm not sure if this one's actually been fixed in the compiler. No idea. But anyway, moving on. So just to summarize, because I've actually talked for a lot longer than I wanted to. So to summarize, we developed from first principles a bunch of constraints on viewpoint adaptation, which made this less restrictive and more permissive to the user, so less fighting with the type system. In addition to that, we made a new operator, the extracting viewpoint adaptation, which allows us to be even less restrictive than viewpoint adaptation in some cases because you're removing the field alias. Additionally, we made a new definition of well-formed visibility, which takes advantage of these new definitions to make itself half the length of the previous definition, which is great in terms of modeling. And finally, we used this definition, as well as a bunch of other stuff, to formally prove that well-formedness is preserved through execution, which is what we set out to show in the beginning, including a bunch of lemmas proven in Prolog, and is far simpler than the existing model, although it doesn't include recovery, but I would like to do that at some point. As always, there's a bunch of content that wasn't covered. I'm not going to go through it. There's all the extensions to the model, like inheritance, things like Prolog, details of the proof, various things to do with temporaries, and so on and so forth. So thanks very much for listening. There's a fun picture here, which I like to show off. On the right, we have all the work I did for my project, which was very, very long and very, very hard, but very, very fun. And on the left, we have the Intel assembly reference manual, all so many thousand pages of it. It was a lot of stuff. So thanks for listening. Any questions? If you're interested in hearing more about this stuff, feel free to get in touch. I hang out on the IRC channel, although I never say anything. Thanks for listening.
Any questions, anyone?
Yeah, I'm actually, I'm curious. So it seems like we would be able to benefit from having in the Pony language an operator for the extractive viewpoint adaptation.
Yeah.
We currently have like the dash greater than for viewpoint adaptation for reading from a field, but it seems like, for example, if you're going to take in a parameter that you need to write to a field that you would want it to be of a viewpoint adapted type, does that seem like it's something that would actually be useful, or is there a reason why it wouldn't be?
Definitely if Sylvan or whoever ever gets around to actually implementing this stuff in the compiler, you would almost definitely need a new operator for the extracting viewpoint adaptation, just because it's a distinct thing now from the existing one. But yeah.
Yeah, okay, and so I guess my other question would be the expansions and the permissiveness of the read viewpoint adaptation. Those haven't been implemented yet either, right, in the compiler?
Not to my knowledge, no. I think Sylvan was understandably cautious about implementing such a thing before we actually went and proved most things in the model, so that's fair enough.
Okay, very cool. Thanks.
Thanks.
Anyone else? All right. Thank you very much, George. Thank you, everyone, for coming. Our next one of these is going to be Thursday, September 1st, same local time for everybody. And Andy Charlie, who's on this call, is going to be talking about the pony garbage collection. So hopefully see some of you then. Thank you very much.
Thank you.
Good afternoon, day, evening, whatever it is. Bye-bye.